All right, welcome to today's video. Today we're going to be learning about conservation of energy. All right, learning targets today are pretty straightforward. You should be able to solve conservation of energy problems dealing with kinetic, gravitational potential, and elastic potential energy. Okay, so first of all, when we deal with energy, we need to understand that there are two different types of forces. All right. Now, if you go on and take AP next year, you will learn sort of more textbooky definitions of conservative and non-conservative forces. For now, first year course, we're going to keep things simple. All right. So, a conservative force for us, basically, a conservative force is going to be any type of any type of force which is responsible for a form of potential energy. Okay. So for us, here's the deal: there are only two conservative forces. Force of gravity is a conservative force because it is responsible for gravitational potential energy, right? Okay, and the force from a spring or a rubber band or something like that would also be considered conservative because it's responsible for elastic potential energy, okay? So that's it. For the purposes of this class, the only two conservative forces are gravity and the force from a spring or something like that, all right? And then non-conservative forces are anything else. Okay, if it's not conservative, then it is non-conservative. All right. So, why does all of this matter? Well, so I guess it was last video, right? We learned about sort of how to do work, and you saw this same slide, I believe. And we learned that when you do work on an object, you're changing the energy in some way. Okay. And what we learned was that. What we learned was that in order for a force to do work on an object, first of all, the object had to be moving, all right? And then number two, this is the one that's going to be super important for these conservation of energy problems. In order for a force to do work, the direction of motion cannot be perpendicular to the direction of the force, okay? So if the object is moving this way and the force is perpendicular to it, then that force is not doing work, okay? So, that's going to be super important here, okay? Now, it turns out that how the work done by a force changes an object's energy depends on whether or not the force is conservative or not, okay? So, it turns out that anytime a conservative force does work, all that conservative force can do is either convert energy either to or from potential energy. Okay? If I hold this pen up in the air, right now it's got gravitational potential energy, right? And so the idea is if I let go of the pen, it falls, right? And what happens is gravity does work on the pen, and what that work is doing is it's converting the gravitational potential energy that the pen has up here, excuse me, to kinetic energy as it falls, right? So we lose potential energy but gain kinetic energy, all right? Similarly, if I throw a pen up in the air, as it's going up, I lose kinetic energy. Why do we lose kinetic energy? Oh, because gravity is doing work against the motion, okay? And so as a result, we lose kinetic energy, but we gain gravitational potential energy, all right? And so this leads us to a really important equation, which I will write now, okay? So it turns out that the work done by conservative forces is equal to the change in the potential energy associated with it. So, you know, if this is gravity, this is gravity. If you have the work done by a spring, that's equal to the change in elastic potential energy, all right? Now, the only difference is the sign is flip-flopped, right? Because if I drop the pen, I lose gravitational potential energy, but gravity does a positive amount of work, okay? All right, so the way that I'll usually denote this is, I guess we'll just do this. The work done by a conservative force is equal to the opposite of the change in potential energy. Okay? All right, so it also turns out that if a non-conservative force does work, then it's changing the total energy. Okay? We'll write that this way. We're going to write the work done by a non-conservative force is equal to the change in total energy. Okay? So if I lift this pen, I'm doing work. I'm giving it more energy than it would have had if I had not lifted it. Okay? So, basically what's going to happen is we are, in the next couple of videos here, we're going to learn about two types of problems. All right? Conservation of energy problems are problems where the work done by non-conservative forces, is zero. Okay? So that's going to be this video. We're going to focus on what happens if the work done by non-conservative forces is zero. That's today's video. Okay? And then the next video will be what happens if that work is not zero. Okay? So, but this equation right here shows us what happens if the work done by non-conservative forces is zero. It just means there's no change in total energy, which leads us to the law of conservation of energy. All right? And the law of conservation of energy says this. If the only forces doing work on an object are conservative forces, then an object's total energy stays the same. So here, if the work done by non-conservative forces is zero, then I guess we could write this one of two ways. Total change in total energy is zero, or total energy is constant, however you want to think of that. Okay? So that is the law of conservation of energy. All right? So all of the examples we're going to be doing today have this. The work done by non-conservative forces is zero. Now, keep in mind, that does not mean necessarily that there are no non-conservative forces. It just means they're not doing work. Okay? So, just a quick reminder, we can talk about total energy, or when we talk about total energy, we're talking about the total of all the different types of energy an object has. Okay? So for us, it's going to be kinetic energy plus, eventually we'll get to rotational kinetic energy. That doesn't come up in this section. Gravitational potential energy, elastic potential energy, and then, conceptually we can talk about electric and chemical potential energy. But for problems, we'll just be dealing with these guys. And like I said, this chapter, because we haven't gotten to rotation yet, we won't even deal with that. Okay? So, this is sort of the classic example, all right? Let me make this so you guys can see it, all right? So this is the classic conservation of energy problem, all right? And you will see this in pretty much any physics class that you take, okay? Different numbers, but same idea, all right? So let's imagine a roller coaster here. For simplicity, let's keep it frictionless, okay? All right, so let's think about what forces are acting on the cart. I don't know if you want to draw this, but I'm just going to, so real quick. So let's imagine an arbitrary point. Here's our cart with our dude in it. Oh, he's having fun because he's on a roller coaster. All right, so what forces are on him? All right, well, so on this cart, there's going to be two forces. There's going to be gravity pulling him down. All right, but that's a conservative force, right? So we're not worried about that. All right, and then the only other force on him, there's no friction. The only other force on him is the normal force. All right, and notice, remember, the normal force is perpendicular to the surface, right? And so that's why I drew that normal force pointing off this way at a weird angle, right? So that it's perpendicular, all right? And so that word perpendicular here is super important, right? Because it means even though the normal force is a non-conservative force, it's not doing work, right? Because a force that's perpendicular to the motion doesn't do work, okay? So this is an example in which the work done by non-conservative forces is zero, which means, therefore, our total energy is constant, all right? So that's going to be the deal, all right? So here's what we can do. So the way these problems are going to be set up, you're going to always be given one point in the object's motion where you know both the velocity and the height, okay? And then you'll be asked to calculate the velocity or the height at some other point. Okay, so here's the deal. We got a 60-kilogram Roy going over the top of the hill, right? He gave you his mass up here. It's going over the top of the hill with this velocity and this height. Okay, so because of this velocity, he's going to have some kinetic energy, right? So let's calculate that. Let's do this. Let's call this point A. So that's the kinetic energy at point A, right? Okay, so his kinetic energy is going to be half of his mass times his velocity squared. So I believe that gives us 3,000 joules, right? Okay, and he's way up on top of a hill. That means that he's got gravitational potential energy here at point A. So let's see, 40 times 60 times 9.8. So we get 23,520 joules. All right? And so those are the only two types of energy he has at that point. And therefore, his total energy at point A is going to be what? 26,520 joules, right? Okay? Now, but here's the deal. Look, our total energy stays constant because the only non-conservative force is normal force. That doesn't do work. So now what I can do is this. I can say, all right, well, here, when the car gets to point B here at the top of this hill, whoa, the question wants us to find his velocity, right? So here's what I know. I know that he's got a height of 15 meters. So that means that his gravitational potential energy at point B is 15 times 60 times 9.8. I'm just calculating, KE and GPE using the equations we've learned earlier in this chapter. So there's his gravitational potential energy. Okay, 8,820 joules. All right. So here's where we get stuck. I always call this the spiral of doom, right? We can't find the velocity because we don't know the kinetic energy, and we can't get the kinetic energy without the velocity. Okay? When you get to that point, when you get stuck where you need your kinetic energy to find your velocity and your velocity to find your kinetic energy, the question you ask yourself is, what do I know about my total energy? All right? And in this problem, we know the total energy is constant, right? So that means that the total energy at B also has to be 26,520 joules. Oh, well, let's see. If my total energy is 26,000 and my GPE is only 8,000, then my kinetic energy must be the remainder, right? So let's subtract this and see what we get. 26,520 joules, and it gives us 17,700 joules of kinetic energy, which you can then use to find the velocity. So V equals the square root of 2ke divided by the mass. So you get 2 times 17,700 over a mass of 60. Don't forget your square root. So let's see, times 2 divided by 60, square root-ified, and you get 24.3 meters a second. Okay? So that is a sort of a classic conservation of energy problem. And it's called a conservation of energy problem because there was no loss of energy, right? All of our energy was conserved. Okay? All right. So why don't you pause the video real quick and take a second and see if you can find the GPE at this point. Okay? I'm sorry, find the height at that point. Okay? While you're doing that, I'm going to erase this green stuff. All right, and let's do the same thing here. All right, so this calculation is going to be almost the same thing, right? So here, let's call this point C. All right, we're up here at the top of the loop. All right, and we're trying to find the height of the loop. So if the velocity is 16, we can call this point C, right? So if the velocity is 16 meters a second, that means there's going to be some kinetic energy, right? So half of his mass times the velocity squared gives you 7,680 joules, right? Oh, to find his height, I need to know the GPE, but I can't find the GPE without the height. So we're in our spiral of doom. So what do we know about the total energy? Oh, it's constant. Total energy is still this number. So we can subtract. You get 18,840 joules, and you can use that then to find your height. So I'm going to take that number and divide it by the mass and divide it by acceleration of gravity, and you get 32 meters. Okay? So the cool thing about these problems is it provides us a way to calculate the velocity of something. So we had already learned how, if you drop an object, to find the velocity that it has after it's fallen some distance, right? And now what we're learning is that even if the thing follows some weird path, if it starts at this height and ends at this height, we can find the velocity at the end, right? Okay? So all right, one other thing to be aware of here, and Okay, sorry. One other thing to be aware of here is this. If there's no elastic potential energy and your energy is being conserved, then you don't need the mass, okay? So in this example, it says, imagine dropping a ball off of a roof that's 3 meters tall. With what velocity would it hit the ground, all right? So the idea is, if we're dropping the ball off the roof, what we know is up here at the top, the velocity is 0, which means my kinetic energy is 0, right? Let's call this point T as in top, and we'll call this point B as in bottom. So the velocity at the top is 0. That means the kinetic energy at the top is 0. The height at the top is 3 meters. So the gravitational potential energy at the top would be mass times 9.8 times 3, right? And so my total energy at the top is mass times 9.8 times 3 is just 29.4. So let's just write that out. So 29.4 times m, right? So that's my deal at the top. Now, when we get down to the bottom, we know the height is 0, right? So that means that my gravitational potential energy at the bottom is 0. My kinetic energy at the bottom is 1/2 the mass times the velocity squared, which means my total energy at the bottom is 1/2 mass times velocity squared. Okay, so what I can do is, I know that this total energy is equal to this total energy, right? So here's my equation. Total energy at the top, 29.4 times m, equals 1/2 mv squared. I know algebra, the m's cancel, and so now I can solve this thing, right? So multiply by 2 and take the square root. So, oops, that's an equal sign. 2 times 29.4 square root. And so you get 7.67, we'll call it. Okay? All right, so what I want you to be aware of here, and I kind of glossed through this, these problems, they're all solved exactly the same way. All of these conservation of energy problems are solved just like this. We identify the important points in the motion, okay? In this problem, there were 2 important points. Top of the ball's path, bottom of the ball's path. At each of those points, I'm going to write out an expression for the total energy, right? Okay, if you don't know the mass, cool, just use m as a placeholder, okay? So you write out an expression for the total energy at each of the 2 points, and then you set them equal to each other, and you solve for the missing thing, all right? In this case, that missing thing is velocity, all right? You cannot solve these problems without writing an expression for the total energy, okay? Finally, this problem was a special case. This was a special problem because in this situation, it was true that the gravitational potential energy at the top was equal to the kinetic energy at the bottom, okay? That is not true as a rule. The only reason that was true here is because we began with no velocity and therefore no kinetic energy, and we ended with no height and therefore no gravitational potential energy, all right? Please, please, please don't be that person who makes the assumption of just setting GPE equal to KE and solving it, because 99% of the time it doesn't work. All right? Okay, I think we got one last example here with elastic potential. Oh, no. Got ahead of myself. All right. So one other example here before we get to our elastic potential energy. So what if instead of dropping that ball, what if we slid it down a frictionless ramp? And I'm glad this is in here. All right? So in that last example, we just dropped a ball off of a cliff and it fell 3 meters, right? What if instead we had a cliff, or had a ramp rather, that was 3 meters tall, and we slid the box down it? Okay? Well, so it turns out the math would be exactly the same, right? Because up at the top, our GPE would be the mass of the box times 9.8 times 3 meters, right? So our GPE would be mass times 9.8 times 3, so you just get 29.4 times m again. Our kinetic energy would be 0, and so our total energy up at the top would still be 29.4 m, right? And then when the box got down to the bottom, now our GPE would be 0, and so our kinetic energy would be 1/2 mv squared again. So you'd still have the same expression for total energy we had before, right? And so you'd set these 2 things equal to each other, okay, and you'd get the same thing, all right? So what that shows us is it doesn't matter as long as the only force doing work is gravity. It doesn't matter how your object moves down through some displacement, in this case 3 meters, right? It's always going to have the same velocity at the end, okay? I didn't say it, but I did write it here. Remember that in this example, we don't need to worry about normal force, right? And that's why this total energy and this total energy are the same, right? All right. Okay, so here's the deal. I think you might have an example that's in your notes with Wile E. Coyote. I'm going to not do that example because there's a small issue with it. And if you don't have it in your packet, then great. But if you do, ignore it. Let's do this. Suppose we've got a spring, okay? So, all right, and let's suppose that the spring has a spring constant of, I don't know, let's say 20 newtons per meter, okay? And what we're going to do is we're going to take a mass, let's say, I don't know, how about 5 kilograms, all right? And we're going to hold this spring here at rest, all right? And then we're going to drop it, okay? And so, you know, what'll happen is the weight will come down, it'll eventually stop, and it'll bounce back up, right? Okay? So let's do this. Let's, first of all, see if we can figure out how far it stretches before stopping, okay? Okay, so what's going to happen is the spring is going to stretch, and eventually it'll get to a point where it stops, right? So let's think about what forces are here, okay? Well, the only 2 forces are going to be gravity, pulling the spring down, and elastic potential energy, right? From the spring being stretched, all right? So what we want to figure out is how far the spring gets stretched. So for us, we're looking for, oops, we'll call it, I don't know, we'll call it delta x about. You can call it h if you wanted to, I guess, all right? Okay, so let's see. So the idea then is at this point, at this first point, all of my energy is gravitational potential energy, right? The velocity is 0, so it's not moving. The spring isn't stretched, so all of my energy here is gravitational potential energy, right? So we'll call this at the top, all right? Oops. Okay, now, over here, we're looking at all elastic potential energy, right? So we'll call this at the bottom. So the idea is at that point, our kinetic energy is 0, all right? So we need to think about what the gravitational potential energy is at this point, all right? So we can pick whatever we want to be a height of 0. So since this looks like it's the lowest point our thing ever gets to, let's call this a height of 0, okay? So that means at this point, at this point here, there's going to be no gravitational potential energy. There's no kinetic energy. There's just elastic potential energy, all right? So I believe in this example, the gravitational potential energy at the top is going to equal the elastic potential energy at the bottom. So GPE at the top is equal to the elastic potential energy at the bottom. So 5 kilograms times 9.8 meters a second squared times the height at the top is delta x, right? Equals 1/2 times k, which is 20 newtons per meter, times delta x squared, right? Okay, so I'm looking at 49 delta x equals 10 delta x squared. And we want to solve for delta x. Okay, well, 0 is a solution, right? But that's not the solution we want. So I think I can divide both sides by delta x and get 49 equals 10 delta x. Divide both sides by 10, and your delta x looks like it's 4.9 meters. And there's your answer. Okay? Notice you do need to put the negative sign in to indicate that it went down, right? Okay. Now, there are certainly other questions that I could ask you here, but there we go. I guess that's that. Okay?